Hi everybody, I'm Riddhi and I'm going to talk about my joint work with Yuval, Alexis, Eyal, Paul and Amit on hard languages in NP intersection coNP and NIZK proofs from Unstructured Hardness. So let us begin by breaking down the title one at a time. Whenever we talk about hard languages, we mean fully specified decision problems as opposed to promise problems which are not NP. NP intersection coNP is the set of all languages for which there is both an efficient NP verifier checking certificates for membership in the language and an efficient coNP verifier checking certificates for non-membership. When it comes to hard languages in NP intersection coNP, we do have a few candidate constructions, but all of them rely on some highly structured assumptions based on factoring and discrete log. We also have a construction based on one-way permutations, but note that the only known constructions of one-way permutations also rely on factoring or discrete log. On the other hand, this is not the case for promise problems, where it's actually quite easy to build hard languages in NP intersection coNP from unstructured hardness assumptions. Moreover, it's quite unclear how hard NP intersection coNP actually is. This is because the strong structure of these very concrete languages may give rise to an efficient algorithm in the future. In fact, we already have efficient quantum algorithms for factoring and discrete log, which makes all of these candidate constructions easy in quantum land. Moreover, we also have some experts who believe that these problems are even classically easy. So here is an example from Peter Sarnak's lecture where he claims to believe that factoring is easy. There are some who actually believe so strongly about this that they have literal rock in their backyard engraved with P equals to NP intersection coNP. As I said before, the very few known candidates for hard language in NP intersection coNP all have a very strong structure. This leads us to ask the following question: can we build a hard language in NP intersection coNP from unstructured assumptions? But what does this even mean? What is the distinction between structured and unstructured problems? Let's begin by looking at random oracles, which are essentially random functions created by sampling uniform random points from a codomain. We follow the standard convention in computer science and mathematics of treating a random function as the ultimate unstructured object, and then classify other objects as being unstructured or structured depending on whether they can be built from a random function. This dichotomy is useful because it separates objects that are easy to construct heuristically from the ones that are not. The most famous example of this dichotomy in cryptography is the distinction between private key encryption scheme and a public key encryption, which was formalized by Impagliazzo and Rudik. The former is typically considered an unstructured object, whereas a public key encryption scheme is considered to be structured. So let us consider a one-way permutation, an injective one-way function which is only slightly expanding. So let's say n to n plus c bits for some constant c, and a length tripling injective one-way function. Now it's clear that a one-way permutation implies a slightly expanding injective one-way function, which in turn implies a length tripling injective one-way function. But the question is there a qualitative difference between these three objects? Now, say that we have a random function from n bits to n bits. The chances that such a function is a one-way permutation is extremely unlikely. Similarly, if we have a function that is slightly expanding, so let's say n to n plus c bits for some constant c, such a function is also unlikely to be an injective one-way function. In fact, we have no known way to construct any of these objects even by post-processing on a random oracle. On the other hand, if we have a random function O that is sufficiently expanding, so let's say n to 3n bits, such a function is going to be injective with an extremely high probability, and this does not require any structure at all. This leads to a very natural divide between these objects where we can now call an injective one-way function which is length tripling to be unstructured, and we can assume that the others are structured assumptions. Now let's take a look at cryptographic assumptions which can be easily instantiated with a random oracle. We know that a random oracle is one-way and collision resistant. Hence, one-way functions and collision-resistant hash functions can be considered unstructured. Moreover, any length tripling or sufficiently expanding random function will be injective with a very high probability. Hence, a sufficiently expanding injective one-way function is also considered to be unstructured. Further, in complexity theory, injective one-way functions imply that UP is not contained in the randomized polynomial time complexity class, where UP is a subclass of NP with unique witnesses. On the other hand, the remaining objects on the screen are either specific mathematical structures like LWE, factoring, and bilinear maps, or are structured cryptographic primitives like one-way permutations, PKE, and OT that cannot be built from a random function. Hence, we create this reasonable partition between unstructured and structured objects. In fact, there have been some roadblocks when it comes to constructing hard languages in NP intersection coNP from unstructured assumptions. For example, we have no known random oracle separations of these two languages, a problem which has been open for the last 40 years. We've also seen that there are some difficulties with this approach, which makes it an all the more challenging problem. On top of that, it has also been shown that there can be no black box constructions of hard languages in NP intersection coNP from one-way functions. A similar impossibility results also holds assuming injective one-way functions plus IO. Now note that IO plus one-way functions implies a lot of cryptographic primitives, so this rules out all of them. Keeping these impossibility results in mind, we now ask whether it is somehow possible to bypass these obstacles and still construct a hard language in NP intersection coNP from unstructured assumptions, specifically from random oracles. Naturally, the moment we talk about constructing hard languages from random oracles, it automatically implies separation of complexity classes relative to a random oracle. In complexity theory, understanding the landscape relative to a random oracle has been the subject of a large body of work originating from Bennett and Gill, who separated P, NP, and coNP by a random oracle. We also know that the polynomial hierarchy is infinite relative to a random oracle. Finally, a very recent work by Yamakawa and Zandri shows a separation between search BQP and search BPP relative to a random oracle. We also have a random oracle hypothesis in complexity theory and cryptography, both of which are generally false, but are possibly true in natural contexts. In complexity theory, this hypothesis says that a random oracle separation of two complexity classes also implies a non-random oracle separation between the same classes. Well, this has been proved to be false for IP and P space, but is plausibly true for feasible complexity classes like P, BPP, and NP. A similar hypothesis also exists in cryptography, which basically says that in natural contexts, one can replace a random oracle by any explicit hash function. I'll now introduce our results. The main theorem says that if there exists injective one-way functions, then with probability 1 over the choice of a random oracle, O, P to the O is not equals to NP to the O intersection coNP to the O. Now, whenever we write this notation P to the O, we mean the class P relative to a random oracle O. In fact, our proof is constructive. So if we take our favorite injective one-way function and instantiate the random oracle with some cryptographic hash function edge, we have a polynomial time algorithm that generates a candidate language in NP intersection coNP, which is not P. In fact, we can relax the assumption of injective one-way functions and just assume that UP is not contained in RP, which is implied by injective one-way functions. The main technical ingredient to construct our language is a non-interactive zero-knowledge proof system in the random oracle model. Note that this cannot be achieved via the standard Fiat-Shamir transformation because the Fiat-Shamir heuristic can only achieve NIZK arguments, which provide soundness against computationally bounded provers. What we require here is soundness against computationally unbounded provers. So we show that there exists an unbounded prover NIZK proof for NP in the random oracle model. Now, if you really do not like random oracles, then we also have an instantiation of a NIZK proof in the uniform random string model from a concrete cryptographic object called the delta-den pseudo-random hash functions. For the sake of time, I am not going to explain what these objects look like or what are the properties that they satisfy, but I must mention some important points regarding this construction. Firstly, on the positive side, a delta-den pseudo-random hash function is unstructured because it is implied by a random oracle. On the other hand, there is a slight caveat here, which is that we do not know how to instantiate these objects from any other unstructured assumptions other than random oracles. So before going into the detailed results, let's look at the definition of NIZK proofs for NP in the uniform random string model. The goal here is for a prover to prove to a verifier V that some instance X belongs to a language L. We are working in a setting where the prover P is unbounded. The verifier V, however, is computationally bounded, and both the prover and verifier share a polynomial length uniform random string. We want this protocol to satisfy three natural properties: completeness, which says that if all the players are honest and X actually belongs to the language, then the verifier must accept; soundness, which says that if X does not belong to the language, then no unbounded cheating prover should make the verifier accept the proof. Finally, we want zero knowledge, which says that there exists a probabilistic polynomial time simulator such that a simulator which gets just the instance as an input can simulate the URS and the proof generated by the prover. Now we can translate this definition into NIZK proofs for NP in the random oracle model, where the first change is the URS disappears and we have a random oracle, so both the prover and verifier have query access to a random oracle. And the definition of zero knowledge has a slight change, where we show that we do not really need a computationally bounded verifier as such. What we want is a verifier which can make only polynomial many queries to a random oracle. When we look at prior works on NIZKs, they can be broadly categorized into two sections: the uniform random string model and the structured random string model, where we allowed this shared string to have some structure in it. In the latter case, we have several constructions of NIZK proofs and NIZK arguments from standard assumptions. Now, when we look at the uniform random string model, we do have some constructions from unstructured hardness assumptions and random oracles. However, all of them only give us NIZK arguments. When it comes to constructing NIZK proofs in the URS model, all the assumptions thus far have been extremely structured. Our construction from random oracles or delta density random hash function gives the first result of a NIZK proof in the URS model from unstructured hardness. Now let's dive into our main separation result. The main ingredients which we use to construct a language is an injective one-way function f and a NIZK proof in the random oracle model for the language L prime, which contains of all instances y for which there exists a pre-image x corresponding to the injective one-way function. Our language L with a random oracle is this tuple y, I, pi, such that y has a pre-image x corresponding to this injective one-way function f, and the ith bit of this pre-image x is 1, and pi is a valid proof that y has a pre-image. Notice that if we remove the NIZK verification and the proof pi from our language, then this indeed looks like a promise problem where we are given a guarantee that y must have a pre-image corresponding to the injective one-way function. So we bridge this gap and remove the promise nature of this problem by appending the proof pi into the statement itself. In fact, we can even get rid of the injective one-way function and a construction would still work completely fine by simply assuming a language L double prime in UP set minus RP. So let's first see that our language L actually belongs to NP. So here is our NP decider that takes as input the instance yi and pi and the witness w. It does the following three checks. It first sees if the NIZK verification goes through. Then it checks if the witness w is indeed a correct pre-image of y with respect to the injective one-way function f. And finally, it sees if the ith bit of the witness is 1. If all these three conditions go through, then it accepts, otherwise it will reject. Now notice that the correctness of our decider simply follows from the definition of our language. If yi and pi belong to the language, then indeed there exists a witness w that will satisfy all these three conditions, in which case our decider will correctly accept. If the instance does not belong to the language, then we can split this into two cases. One, where y has a pre-image, and the other case where y does not have a pre-image relative to the injective one-way function f. In the second case, no matter which witness w you pick, the second condition will never go through. Hence, our decider will always correctly reject. Now let's say that y has a pre-image w, and the ith bit of that pre-image is indeed 1. In that case, it must be that the NIZK verification does not go through. Otherwise, by definition, the instance yi and pi must have belonged to the language L. Now let us look at our second containment result. Note that this is not an unconditional statement. Here we say that if our NIZK is perfectly sound, then with probability 1 over the choice of a random oracle, our language L belongs to coNP. Note that we have a slight asterisk beside perfectly sound because we do not quite achieve perfect soundness. What we achieve is soundness with probability 1 over the choice of random oracle. Now, by definition, if our language L belongs to coNP, it means that the complement language must have an NP decider. So in our case, the complement language looks like the following. It contains of the tuple yi and pi such that either the NIZK verification algorithm outputs is 0 or y does not contain any pre-image x whose ith bit is 1. So here is the coNP decider for our language, which does the following. It first checks if the NIZK verifier verifies. If it does not, then it simply accepts. If it does, then by the perfect soundness of the NIZK proof, we can know for sure that there must exist some x such that f of x is equals to y. Now this x is unique because f is injective. So we can expect this x to be the unique witness w. Now all the decider needs to do is check if f of w is indeed equals to y and if the ith bit of this witness is 0. If both of these happen, then it just accepts, otherwise it's going to reject. Finally, let's show that our language L is indeed hard. Specifically, we show that if our NIZK is 0 knowledge, then with probability 1 over the choice of our random oracle, L does not belong to P. To prove this, let's start by contradiction. So let's say that probability over the choice of the random oracle, L belongs to P is greater than 0. Now we import a theorem from Bennett and Gill that says that if that indeed is the case, then there must exist some polynomial time Turing machine D which decides this language L with probability 1 over the choice of the random oracle. So it's an amplification result. Say such a decider exists. In that case, we can show that with probability negligibly close to 1, one can invert this one-way function f. So let's see how it works. Say you have an inverter that gets as input y. For every bit I, it does the following. It first triggers an NIZK simulator to simulate the proof pi that y has a preimage. Then it runs the decider d with input yi and pi and gets some output. It then sets the ith bit of the preimage to be the output that it received. It runs this for all the bits. Eventually, the inverter has created some preimage which it then outputs. So why is this the correct output? So say that if pi was indeed the real proof, then this decider would correctly output xi all the time, and that follows by the correctness property of the decider. Now at a high level, the idea is that due to zero knowledge, the simulated proof also mimics the real world proof, which will make the decider D act similarly in both the cases. Hence here as well, the output xi would be correct. In the language which we constructed, the crucial tool which we used was NIZK Proofs in the random oracle model. So now I'll talk about how we constructed this NIZK proof. To get our NIZK proof as a starting point, we use the construction of FLS9P, which gives a NIZK proof for NP from one-way permutations in the URS model. And roughly the goal is to somehow replace these one-way permutations with a random oracle. In the original FLS construction, they begin with a NIZK proof for NP in the hidden bits model, then they instantiate the hidden bits with a URS and one-way permutation. In our setting, we modify the hidden bits model to something which we call the Z-tamperable hidden bits model. We build a NIZK proof for NP in this new model. Then we instantiate the Z-tamperable hidden bits model with a random oracle. Let's begin by reviewing the hidden bits model. So in that model, we assume that there exists a uniformly random hidden string up in the sky. The prover has access to the entire string in the open. However, the verifier does not know what the string is. So in this protocol, the prover P sends some proof of whatever statement it wants to prove, along with indices of the hidden bits that it wants the verifier to see. So now the verifier only gets to see the hidden bits of the indices chosen by P. And finally, the verifier must accept or reject the proof as usual. In FLS, they showed how to instantiate the hidden bits with the URS using one-way permutations. Say you have some one-way permutation O and a uniform random string y1 through yn. Here you can consider each yi to be some polynomial length strings from the range of the one-way permutation. So you first invert these yi's to get some xi such that O of xi is yi. Then you compute the hardcore bit corresponding to these xi, and that hardcore bit is said to be the hidden bit. So the hidden bit Ri is equals to the hardcore bit computed on xi. Now, why does this work? So O is hard to invert, which means that the verifier V cannot learn anything about the hidden bit string just by looking at the uniform random string. And they are pseudo-random because they are hardcore bits. So we are good. From a prover's point of view, the prover is unbounded. So the prover can actually compute these preimages xi by brute force. And once it computes these preimages and the hardcore bits, it just sends an xi comma ri to the verifier, which can now check if O of xi is actually equals to yi and if the hardcore bit was correctly computed. Now let's say we just want to replace the one-way permutation with a random oracle directly. This immediately creates a couple of issues. The first one being that yi's need not belong to the range of the random oracle O, because a random oracle might not be surjective. In that case, there might be some yi's in the uniform random string which do not have a preimage, hence the prover cannot compute the hidden bits correctly and we lose completeness. So one might suggest that what if we shrink the size of the codomain such that the random oracle becomes surjective with a high probability? Sure, we can do that, but that creates another problem where we now might have some yi's which have multiple preimages. If that is the case, then there can be two x's that map to the same y, in which case one y will actually create two different hardcore bits, which might not be identical, in which case there is no way for the verifier to check if the hidden bits which was opened by the prover was actually the one which was used in the proof or not, in which case we lose soundness. To solve this, we have the following new idea, where we say that instead of inverting the y's and then creating the hardcore bits, we do the following. We directly set the hidden bits to be 1 or 0 depending on whether these y's have a preimage corresponding to the random oracle or not. So the hidden bit Ri becomes 0 if yi has a preimage, otherwise it becomes 1. Now let's analyze what we have here. So for a verifier, there is no way for them to determine whether a certain yi has a preimage or not because they're computationally bounded. So the hidden bits stay hidden and there doesn't seem to be any problem here. Now, because the prover has unlimited access to the random oracle and is computationally unbounded, it can always brute force and check whether a particular yi has a preimage or not and respond accordingly. Now, if a yi does not have a preimage, there is not much a prover can actually do, because it can never provide an xi which would correctly match to the corresponding yi, hence it must set r sub I to be 1 in that case. However, a major problem arises when a yi actually has a preimage, because the prover can always claim that the yi does not have a preimage even if it does, and there is no way for a computationally bounded verifier to check whether the prover is answering correctly or not, in which case we end up losing soundness completely. To solve this issue, we define a new model which captures exactly this behavior. This new model is essentially same as the hidden bits model, except that the prover P can now lie about the hidden bits when the hidden bit is 0. So if Ri was 1, then it must open Ri to be 1. If it was 0, then it can open Ri to be either 0 or 1. This essentially captures the ability of a dishonest prover to lie by saying that there is no preimage when there actually was one. And we call this model the Z-temperable hidden bits model because it is similar to the Z-channel information theory. Well, it turns out that the prover actually cannot lie too much. Because the random oracle has some very nice distributions, it is easy to compute the probability that a randomly chosen point in the codomain will belong to the range of a random oracle. Using these probability computations, a verifier can run some statistical tests on the distribution of the hidden bits that it receives and check if there are too many ones in it, in which case it can catch a cheating prover. Due to lack of time, I give a quick overview of the key ideas in their construction. So we start with the hidden bits model from FLS and change the parameters to make sure that the cheating behavior of the prover gets easily detectable. Next, we allow the verifier to run some statistical tests based on the distribution defined by the random oracle. This allows the verifier to check whether the number of zeros and ones opened by the prover actually matches the correct distribution. If not, then it will reject. I would like to point out that a blanket statistical test checking the number of zeros and ones does not really work here, and we need to carefully set the tests for the prover to be caught. Our analysis shows that the number of zeros that a prover needs to flip to 1 in order to cheat is way higher than what the permissible limit is, and this allows the verifier to catch a prover with overwhelming probability. Finally, I leave you with some open problems. Firstly, the question is, can we get an unconditional random oracle separation of P and NP intersection coNP? Note that our result relies on the assumption that UP is not contained in RP, so can we get rid of that? Secondly, we show an instantiation of a NIZK proof system in the uniform random string model from an object called delta-den pseudo-random hash functions, which I unfortunately could not elaborate upon. So the question is, can we instantiate this from standard unstructured assumptions other than random oracles, which we do not know of yet? Finally, this might be of independent interest as well, but can we build efficient prover NIZK proofs from random oracles? Thank you.